We're going to talk about the second derivative and how we can use the second derivative to talk about certain things of a function. Before we do that, I want to first draw a couple of pictures and remind you some things about concavity. There's something called concave up and concave down. This particular graph is concave up. This particular graph is concave down. The next graph is concave down, and then concave up. The next graph is concave down, and then concave up. Something else important to understand, this place where it changes is called the point of inflection. Usually I abbreviate that with POI. The point of inflection is not always easy to find, especially when you're looking at the last two types of functions. Finding that place where it changes, usually it's kind of close to being in between the max and the min if there is one. But that's how the second derivative is going to help us. The second derivative actually shows me the concavity of the function, and then where concavity changes is where the points of inflection are going to be. So we kind of do something similar to the way that we use the first derivative test, where we find a number line, set it equal to 0, find the positives and negatives, except when we plug in functions for this one, we plug it into the second derivative instead of plugging it into the first derivative. So here's a function, and I want to know about its concavity, and I want to know about the points of inflection. So here's f of x. You start off by finding f prime of x, and then this time we find f double prime of x. So f double prime is 2x. We set that equal to 0, and you get 0 is a critical point of the second derivative. Alright, and then you plug in values below 0 and above 0 into the second derivative, because we're wanting to know what's going on with the second derivative. I plug in a negative and I get a negative, plug in a positive and I get a positive. What that tells me is that f of x is concave down from negative infinity to 0, and it's concave up from 0 to infinity, and that there's a point of inflection at x equals 0. Alright, so here we have f of x equals 6 over x squared plus 3. Let's find the first derivative. Bottom times derivative of the top minus top times derivative of the bottom over the bottom squared. So we have negative 12x over x squared plus 3 squared. Alright, we've got to find the second derivative. I'll do that on another page. We've got to do the quotient rule again. Bottom times the derivative of the top minus the top times the derivative of the bottom. There's times a 2x there, over the bottom squared, and I know that's yucky. You can factor out a x squared plus 3 out of the top. When you do that, you're left with negative 12x squared minus 36. 2 times 2 times 12 is negative 48. X squared, and this negative here in the middle is going to make that be a positive. That's still over x squared plus 3 to the 4th. Alright, we get 36x squared minus 36. Again, I know this is yucky, but I wanted you to see a yucky one as we're doing this. Alright, and last thing I'm going to do is I'm going to factor out a 36 on top, just because it's going to be easier, because you have to solve where the bottom and the top is equal to 0. On this one, the bottom and the top is equal to 0, where x is plus or minus 1. This doesn't really give me anything because it would be an imaginary solution. Alright, so I'm going to put negative 1 and 1 on the number line. And I'm going to use the second derivative. So I'm going to use this right here, and I'm going to plug in values. So if I plug in 0, I'm going to get a negative. If I plug in negative 2 and positive 2, looks like I'm going to get a positive on top and the bottom. So this means that f of x is concave up from negative infinity to negative 1 and 1 to infinity, concave down from negative 1 to 1, and there's a point of inflection at x equals negative 1 and 1 because concavity is changing, because it's changing from positive to negative to positive. Now I want to show you just a couple more examples. On these examples, I want you to know that I've already found the second derivative. Oops. I don't know what the original looks like, but here's the second derivative. And I set it equal to 0, and I made a number line. So I'm just wanting to show you what the number line looks like and how that you can use that number line to help you. So what this tells me is that f of x is concave up from 0 to infinity and concave down from negative infinity to 0. And notice the only place that concavity changes is at 0. So 0 is our point of inflection. There's not a point of inflection at 2 because concavity is not changing, it's staying the same at positive and positive. One last example. We're going to let f double prime of x equals x times 2x plus 1 over x minus 3 squared. Again, this is already the second derivative. I've already found it for you. You set the bottom or the top equal to 0, you get negative a half and 0. Set the top equal to 0, you get 3. Plug in values into that derivative, you'll get positive, negative, positive, positive. So this graph is concave, or f of x is concave up from negative infinity to negative a half, and 0 to infinity, 0 to 3 and 3 to infinity. It's concave down. Let's see, where can I write this? Concave down from 1/2 to 0. The only points of inflection are at negative 1/2 and 0 and not at 3. And the reason for that is because we're changing concavity there. Notice at 3, concavity is positive on both of them. Second derivative is positive on both. So the concavity does not change. Here's your one to try. Let f of x equal x to the 4th minus 4x to the 3rd. And figure out concavity and points of inflection.